Hello everyone, this is Dr. Mohammad Kabiruzzaman, Assistant Professor, Electrical and Electronic Engineering Department, Faculty of Engineering. Can you hear me?
Yes, we can hear you.
Yes.
And welcome to the virtual session, day 1, parallel session 1-3, D1P13 of the ICREST 21. I am your host and co-chair for this session. This is the first day of the conference and the current time is 10 a.m. Bangladesh Standard Time. This session has one invited speaker and 6 papers, and the paper IDs are 64, 184, 249, 309, 378, and 392. This session will be shared by Dr. Mainul Hossain, Assistant Professor, Department of Electrical and Electronic Engineering, University of Dhaka, and co-chaired by me. The coordinator of this session is Mr. Nafiz Ahmed Sisti, Technical Program Chair Coordinator, ICREST 21, and Associate Professor of AIUB. We also have with us Mr. Sujan Hauladar and Mr. Qazi Ahmed Asif Fuad. Both are Senior Lecturer of AIUB as the co-hosts of this session. The authors may choose to present live or run the pre-recorded video by us. There will be a 3 to 5 minutes question and answer session after each presentation. Please turn on your microphone and video and introduce yourself during question and answer. Please note that whole session will be recorded. Dear participants, besides live questions, you can write questions to presenters in the chat box. Write paper ID and question. Session chairs will pick important questions from there if time permits. We request all the authors of this session to be present till the end. Now we will have 2 group photos with permission from the session chairs, one with session chairs and presenters, and other one with all present in the room. At the end of the session, we will have another group photo with all presenters, participants, session chairs, guests, and hosts. So now I am requesting you to turn the video on.
Kindly turn on the cameras, please. We still see half of the people not turning on their cameras. Please kindly turn on the camera. Sir, should we take the image?
Yes, please go ahead.
Okay, we are taking the first, we are taking the picture. Please stay calm and remain silent for a few seconds. Thank you. We have taken the picture. Sir, you can move to the next phase.
So thank you very much, Kazi Ahmed sir. So please turn camera off and mute your microphone. Now I am inviting to the invited speaker, Dr. Mainul Hossain, to start his talk, which is entitled Hyper Scaling for Emerging Nanoelectronic Devices. Dr. Mainul Hossain received the PhD degree in electrical engineering from the University of Central Florida, Orlando, Florida, USA in 2012. He was with the Global Foundries Advanced Module Engineering, Malta, New York, USA between 2012 and 2017. Then he joined University of Dhaka in 2017, where he is currently an assistant professor in the Department of Electrical and Electronic Engineering. His current research interests include emerging nanoelectronic and nanophotonic devices and material science. He holds one US patent and has co-authored one book chapter and numerous research papers. Now I am welcoming to Dr. Mainul Hossain to start the talk. Thank you.
Uh, Thank you, Dr. Kabir Zaman. So let me share my screen first. Can you see my screen?
Yes,
Yes.
we can see.
Yes.
Okay. Okay. Thank you. So thank you, Dr. Kabir Zaman, for the nice introduction. And it's a pleasure to be here today, although I wish we could be there physically, but due to the pandemic, we are holding the virtual session. But anyway, thanks to the ICREST organizers for inviting me. So I'm going to talk about hyperscaling for emerging nanoelectronic devices today. Okay, so Dr. Zaman has already given a brief introduction about me. So I just like to mention that I come from a industry background, basically working with two giant fabs in the US, IBM fab in East Fishkill, New York, and the Global Foundries fab in Malta, New York. So where I was part of the R&D team working on next generation computer chips. So back in 2007, I moved back to Bangladesh from USA, and I call this a 60 degrees transition because where I was in New York, upstate New York, it was like minus 30 degrees Celsius, and then I came back to Dhaka, it's plus 30. So I call this a 60 degrees transition. So, so what are we going to talk about today? So I'm going to give you some basic idea about what the semiconductor industry does and what they are doing right now. Okay, so I'm going to give you some idea about the industry landscapes. Then you might all have heard about Moore's law. So I'm going to talk a little bit about Moore's law. What are we doing in the industry with that? And then we'll go into today's topic of hyperscaling, talk about some energy efficient devices, and then I will talk about my research that I've been doing here in Dhaka, and then present some future outlook. So I hope you'll stay with me for the next 25 minutes, and then we'll take some questions. Okay, so let's take a look at the chip industry first. Okay, now, I mean, the semiconductor chips, I mean, they have done a huge revolution over the years. I mean, we might not realize it, but if you look back into the history, like back in the maybe early 70s or late 60s, uh, I mean, the Apollo landed on the moon, right, 1969, and the computers that they used for that purpose were much, much less powerful than what you have in your pockets right now. So your cell phones have chips which are more powerful than what were used back in the 70s to send a rocket to the moon. Okay, So that's a remarkable way of looking into it. Okay. Now, coming back to the industry tree, the semiconductor industry as a whole can be divided into like three major categories. We call them, let's start from the bottom of it. We call them the IDM or independent device manufacturers. You have heard about Intel. Intel is an India own chips and they make their own chips. Okay. So that's called independent device manufacturers. And Samsung, well, Samsung is also independent to some extent. You have Toshiba, you have Micron, and SK Hynix and all. And then you have another category which we call the foundries. They make chip for IDM and IFM. Okay, what is IFM? I'm coming to that. IFM means integrated fabless manufacturers, like companies which which work with semiconductor chips, but they don't have fabrication facilities to make them. For example, Apple. Apple doesn't have a fab. They have $500 billion in their bank, but they don't want to open a fabrication facility to make chips. Okay, so that's where foundries come in. Like foundries, like for example, Global Foundries, where I used to work with, uh, and then the largest foundry is TSMC in the world. So what they do is basically they take orders from IFM and sometimes from IDM, because if the IDM want to produce more chips, okay, they don't have the capacity, they give it to the foundries. So foundries produce chips for both IDM and IFM. Okay, so Global Foundries has a background of connecting with IBM, because in 2015, uh, Global Foundries purchased IBM. So basically, these two companies became one company back in 2015. Okay, so coming back to the industry model, the largest chip foundry in the world is in Taiwan. It's called the TSMC, Taiwan Semiconductor Manufacturing Company, and their biggest customer is Apple. All the Apple products that you see, iPhones, iPads, okay, MacBooks, okay, all the chips are made by TSMC. So just to give you some idea how much money they make. So back in 2019, their net revenue was $106 billion. Now I put this slide especially because I want to just make a comparison, maybe be in the hoping that somewhere some policymaker would see this and start thinking about it. If you put in context, Bangladesh is like 7 times larger in terms of its population and 4 times larger in terms of the land area compared to Taiwan. But are we doing anything with the chips semiconductor industry? The answer is no. Okay, so something to think about. Okay, now coming back to the Moore's law, you all have heard about Moore's law in your basic electronics course or device course. Okay, the number of transistors gets doubled every year or like every 18 months. So you have basically heard about it. So it's not basically a law, it's just a hypothesis or a prediction that Moore made. Okay, so ever since Moore's law came into the picture, people have been saying that, oh, it's gonna die sometime, it's gonna crash, we have to look for new things, we have to invent new devices, as and also the number of people predicting the death of Moore's law doubles every 2 years. This is a funny comment made by Peter Lee, who's the VP of Microsoft Research. So here you can see some articles else that were predicting, oh, Moore's law is ending, and we have to find some new ways, blah blah blah. But in reality, if you go into the industry, uh, the Moore's law will survive. Okay, so I'm gonna show you how, and that's where hyperscaling comes in. Okay, so no matter how much we say Moore's law is ending, it's not going to end. So this is what it says, that Moore's law is not dead, it's not dying, and it's not even sick. Okay, so I tell you why. So this is Jensen Huang, who, I mean, he's the CEO of NVIDIA, and he's looking, he's showing you a chip, a graphics chip, a GPU processor, and this one has 21 billion transistors in it. 21 billion. Okay. Okay. If you try to, I mean, imagine how big this number is. Think about the neurons in your brain. So your brains have 86 billion neurons. So it's like 1/4 the number of neurons that you have in your brain. Okay. And what's the world population? Like 7.8 billion, right? So it's even larger than that. So all the people in the world, if they were transistors, okay, 3 times that would fit into this chip. Okay. And that's still Moore's law. Okay. But it's not conventional scaling. This it's not doesn't mean that you just reduce the size and bring it to this scale. Okay. So this is from the IEDM meeting in 2009. Okay. IEDM is the, is International Electron Device Meeting, and it predicted a roadmap for Moore's law that's going to last all the way till 2029, maybe beyond, and we can go all the way up to 1.4 nanometer chips. Okay. Now, this is conventional Dennard scaling, which you might have seen in your textbooks, that you scale everything, you scale the gate, you scale the channel, you scale the interconnects, like by a fixed amount, right? By a factor of k. So everything is scaled, right? So that's the geometric or conventional scaling. Okay. Now, it's uh, is going on for some time, since about 2003 or so. So starting from 2003, uh, I mean, problems started to happen, right? What kind of problems? Like leakage, okay? And then people, I mean, as you scale the device, okay, you keep losing gate control, your device performance goes down. So all this were happening with scaling in the background, okay? So people came up with some ways, and this happened actually in the industry, to combat these issues that came with conventional Dennard scaling. Okay, so I call this the breakthroughs in semiconductor technology. So first was the strained silicon, then the high-k metal gate, and then the FinFETs. Okay, so let me just quickly go through. So strained silicon is basically you have your source and drain regions, and you put silicon germanium on top of silicon here. It creates a strain in the channel and increases your mobility. High-k metal gate, you replace the polysilicon with a metal, and it increases your current carrying capacity. So this were like 2003, 4, 2008 time frame. And then came the FinFET, which actually changed the whole scenario. So before, devices were two-dimensional, because it means you have a gate and you control the current with the gate voltage. But FinFETs, when they were invented, it came with the idea of having 3 gates instead of 1. So imagine this like a tap, right? Like a faucet. You have 3 taps over here, and you can control. If you have 3 taps, then you have more control on the water flow. Similarly, if you have 3 gates controlling the channel, then you have more control on the gate. And obviously, this increased the device performance, made it faster, and made it consume less power. So all this happened with FinFETs. Now, as channel I mean, shrinking was happening, FinFETs came in, all this, we were putting more and more chips into the, I mean, more and more transistors, sorry, into the chip. So what was happening is that, okay, you were shrinking the transistor size, but at the same time, you were increasing the number of transistors in a chip. So these effects actually, basically, they counterbalance each other, okay? So what was happening, the rate at which you were scaling the transistors was much lower than the rate at which the number of transistors were increasing. So you see the number of transistors increased by a factor of, let's say 1/7, okay? So what happened, And with this is that problems like short channel effects started to be a big problem. Then you had power dissipation, because yes, your chip size is increasing. I mean, transistor size is decreasing, but you are putting more transistors in the same chip. So overall, your power dissipation went up. Okay, and obviously the process became more complex. So in this graph, we can see that how this problem occurred, that when you scale, do the conventional scaling, you are losing your current on-off ratio. Okay. A possible solution would be to have a device that doesn't have degrade your off current, but still maintains a higher on current. And those are called the steep slope devices. So this could actually be a possible solution. So heating is a big problem, as you can see. I mean, there are some funny blogs out there saying you can cook pancakes and cookies on your CPU. To put this into today's contents, by the way, I borrowed this slide from one of Professor Saif Salahuddin's talk at UC Berkeley, where he presented the impact of big data and IoT on the computing thing needs. Okay, so we all are connected to the web. We know about IoTs and clouds and all these things. Okay, now there's a workshop back in 2018 in DOE, Department of Energy in the US, and it showed that the amount of data that is generated in the accelerators. You know what are accelerators? Like they're used to study fundamental particles, right? So that goes up to like 700 petabytes of data. This is predicted to be produced uh, in the future, and the amount of research that's going on. So this amount of data, 700 petabytes, peta means 1E15, right? So if you want to process this data, let's say at the rate of, let's say 50 picojoules per bit, that is the energy you need, or the power you need to process this data per bit of this data. Okay, so if you do it at this rate, it will require 50 kilowatts of energy. So that's a lot of energy. Okay, you cannot have your computers consuming this much amount of energy, then it will be a disaster. Okay, now when you do a tweet, I mean, some of you might have used Twitter. Okay, so if you tweet, you actually I mean, you can convert this as process into the amount of energy that is consumed. Okay, and that is converted to a carbon footprint. So if you do this, so one tweet takes like 0.02 grams of carbon dioxide emission. Okay, if you convert it to the carbon footprint terms. Okay, now you know this guy. Okay, he loves to tweet, right? And hopefully you won't see him anymore, but probably this is the last time. So it was predicted that in the first few months of his presidency in 2016, he made 920 tweets. So that was again retweeted because he's really popular, and it became like 100,000 tweets. And Professor Salahuddin from Berkeley, he calculated this and showed that this amounts to 1.8 metric tons of carbon dioxide emission. Okay, so if you compare this with the US consumption, a typical household normally uses 4 metric tons of carbon dioxide per month. So, I mean, saying all this means when you go to the social media, you do Facebook, you do tweet, every time you're consuming a lot of energy. We want to bring this energy consumption down and make our devices more efficient. That's where hyperscaling comes in. So, geometric scaling, this era is basically pre 2003, so it has ended. Okay, it was just simply scaling the geometric dimensions. Now we go to effective scaling. Okay, and there you talk about strained silicon, like I said, high k metal gate. Okay, and FinFETs, all this come into the effective scaling. This is where we are right now. Okay, and the future is looking into hyperscaling. That means we're looking at new types of device physics. We're looking at embedded memories, and we're looking at three-dimensional as you can see on the picture at the right, three-dimensional integration. Okay. Okay, so this is the hyperscaling, putting into context. Okay, so we have new device architecture that's coming in. We have new materials to explore, and we have new lithography techniques and all. So I'm not going to go into the details, but that's where the innovations will continue. Okay, and that's what we mean by hyperscaling. So all this is done to push silicon to the limit. We're not yet looking into carbon nanotubes and all. So this is just a summary of hyperscaling. We have new device architecture. We're looking at new materials. We're looking at new lithography techniques, because we want to stay with silicon. We don't want to go to carbon nanotubes or graphene. Okay. And one of the enabling technologies that make it possible is the extreme UV technology, where compared to conventional lithography, where you use light, okay, ultraviolet light, here you use ultraviolet in the extreme wavelength range. So conventional lithography is 193 nanometers, and this is down to 13.5 nanometers. Okay, so you can make feature size even smaller. So things are going on, and in the background, this is 7 nanometer technology. By the way, 7 nanometer is approximately, you can say it's the gate length. Okay, and this is already being explored since 2015 by IBM. Okay, and then TSMC actually taped this out, or they made it to production in 2019. In fact, the Apple A13 chip has 7 nanometer TSMC FinFET. Okay, then people are also doing research on 5 nanometer in the industry. So this is IBM picture. I was part of this group where they developed this gate all around nano sheet transistors back in started from 2014 or so, and this was published in 2017. And this is basically where you have the channel and you put a you wrap the gate around it. Okay, so we have new types of device architectures. We talked about the FinFET, where the gate surrounds the channel from three sides. You have the nanowire FET, where you have the gate wrapped around the channel. Okay, and the latest thing is the nano sheet transistors, where you have basically stacked sheets which are wider in length and on top of each other to increase the current carrying capacity. And this is the 3 nanometer gate all around process development kit for Samsung's chips that's coming up. Okay, where is it going to stop? Okay, well, this is predicted. This is from an online news portal, very latest August 2020. Okay, just few months back, where TSMC announced 2 nanometer chip factory. Okay, so I mean, industry people are still sticking to silicon till the 2 nanometer node. Okay, now the next I have around maybe another 5 or 6 minutes. I'll quickly talk about what research we are doing here in Dhaka University. So as I said, like one of the major components of hyperscaling is having a sub-Boltzmann field effect transistors. So sub-Boltzmann means that your subthreshold swing is less than 60 millivolts per decade. Now, if you take conventional transistors, shows the power dissipation that has the trend for the power dissipation over the years. And you can see that the power dissipation is increasing. Okay, static power and dynamic power. Okay, now, but this power dissipation is actually hits a benchmark which is known as the Boltzmann constant. It depends on the subthreshold swing. Since your subthreshold swing at room temperature cannot go below 60 millivolts per decade, you cannot reduce your power beyond a certain level. Okay, that's where your negative transistors come in. So if you see, this is the red curve is your conventional MOSFET. Okay, if you want to reduce the power, you need to reduce the uh, supply voltage, right? So if you do that, you can reduce that, but your off current will also increase, which will kill your on off ratio. But if you have a negative capacitance transistor, you can achieve that same on off ratio or better on off ratio, but with a reduced turn on voltage. Okay, that's the advantage. And what is the physics behind it? So basically, this is your MOSFET. This is the phi S. This is the interface of the semiconductor and the oxide. And the voltage drop over here, you can calculate using a simple voltage divider law. So if you do that, you end up with this expression. I'm not going into the math, but you end up with this expression of which contains the ratio of the semiconductor capacitance versus the oxide capacitance. Okay. So and this is 60. This comes from the Boltzmann statistics. Okay. Now this is 60. This is fixed, right? The only way you can reduce the subthreshold swing. Okay. You see that this part of this equation is always greater than 1. Okay, and this is 60. You cannot do anything with this. This is fundamental limit, right? So the only way you can reduce your subthreshold swing, and reducing the subthreshold swing will reduce your power. The only way you can do that is if this term is less than 1. And this is possible to have this less than 1 only when either the semiconductor or the oxide capacitance is negative. And that's what happens over here, that you replace the oxide with a ferroelectric material which has a negative capacitance, and this brings down your subthreshold swing. So that's about the physics explained over here. I'm not going to go too much into the details, but this is your typical charge voltage characteristics for positive capacitance. This is for negative capacitance. And if you plot the energy, you know, energy is q squared by 2c, you get this parabola curve. And this is for the negative capacitance. But one of the problems, with the negative capacitance is the stability. Now, if you look at this, typically it's like lead titanate crystal. The central atom is a little off-centered, which creates the polarizations. Okay, uh, it could be either positive or negative polarizations, and then you can actually uh, plot this energy landscape. Okay, so if you do that, you see that this region over here, which we just saw in the previous curve, this is the negative capacitance region where your capacitance is negative. But this is energetically, this is unstable. If you want to put a charge over here, it won't stay. It will just fall down because that part is unstable. So what you do to make this stable there is that you combine the ferroelectric with the oxide capacitance. You add this to the oxide has a positive energy landscape. When you combine these two, then at this point you end up with a stable energy where your charge can stay. So we have explored that in our research with emerging FET structures like gate-all-around and FinFETs. Okay, and although negative capacitance phenomenon has been done previously by researchers all over the world uh, using simple planar transistors, we here used simulations, and basically TCAT simulations, to show how this negative capacitance will affect our future devices. That means the devices which in the industry is considering for next generation electronics. So we showed that if you put this in a FinFET, you have 45% reduction in subthreshold swing compared to normal FinFET. If you put this in the nanowire, you get 68% reduction in subthreshold swing compared to the baseline. Okay, and then we followed this up with further studies. This was published in IEEE TED recently, and here we played around with different kinds of nanosheet transistors. And Samsung, TSMC, they are looking into this nanosheet transistors as for their future devices like 3 nanometer and 5 nanometer mode. But they have not explored how the negative capacitance effect will play into this. Obviously, these devices itself are really good for scaling and for electrostatic properties, but putting negative capacitance in there makes it much better. Okay, so I'll just take one more minute to finish up. So is it really the end of silicon, right? Right. Well, if you think in terms of chips, the answer is no. In fact, my colleagues at IBM used to say that silicon is going to last for another 100 years at least. Okay. So what do we have then for graphene and MOS to all these devices? Okay. This will have other applications, may not be directly used in the chips, but let's say for sensors, for optical detectors, and all, it might have some use. And also, like if you want to do some heterogeneous integration with different types of devices, it might find some use. But if you think about large scale, that's probably not likely in the next at least maybe 50 to 100 years. Okay. So but people are still working. This is from the Vienna University of Technology. They made a microprocessor based on two-dimensional semiconductor, which is MOS2. This is a work from MIT. They made a carbon nanotube microprocessor. Okay, so people are still working on it. Okay, so that brings us to the end of the presentation. This is my group at Dhaka University. This is, I call this the end. Okay, it says the emerging nanoscale devices. And I'd like to thank my students, my collaborators. I do collaborate with a lot of universities at home and abroad, sharing ideas, sharing resources. Yes, and thanks to them. And a big thanks to AIUB and the Faculty of Engineering at AIUB, IEEE Bangladesh section, the technical co-sponsor for this. And if you are not asleep yet, if I didn't bore you that much, right? If you're still awake, uh, then yeah, you may ask questions. Okay. Okay. Thank you.
Thank you very much, Dr. Mainul Hossain, for your wonderful talk. And you have shown the industry perspective, academic perspective, and you are doing a lot from Bangladesh, and you are doing the, especially the simulation, right? So
Yeah.
now I would like to invite the questions from the participants. So if you have questions, please unmute your microphone and ask the questions, or you can also write your questions in the chat box.
Any questions from the students or faculties?
Okay, I think I should start first. Okay, then maybe
Yeah. Yeah. Sure.
any of you the questions. So we know that the people are very aware about the Moore's law, and
Mhm.
that the silicon is maybe going to be finished. But we are seeing that very interesting. The Moore's law is not finishing actually. But so would you please tell us some over what are the overcoming the options? That means what are the options we can use with silicon or without silicon to overcome the Moore's law?
Okay. So basically, there are three areas, as I showed in one of my slides. Let me go back a little bit. Uh, here. So basically, here are the options. So one thing people are doing is they're looking at the device architecture. The people who design the chips, they basically they are looking at different types of architectures. For example, FinFET came in back in 2011, and in the next 9 years, people came up with the idea of nanoware FETs, and now they're doing nanosheet FETs. So there is also some 3D integration that is being talked about, like where you can have two chips is on top of each other. That that is three-dimensional integration that will come next. So that is the device architecture. Then they're looking at new materials. New materials doesn't mean to replace silicon, but maybe to add or to combine with silicon. For example, I talked about ferroelectric. So ferroelectric is not replacing silicon. It is just adding gate stack. I mean, it is just adding the ferroelectric into the gate stack of the device. And aluminum doped hafnium oxide is a ferroelectric. Then you have people are trying like also 3,5, like where they want to use the 3,5 material in the channel. Okay, but your substrate will be like silicon, integrating that. And then the third option is doing different like technologies, right, uh, which allow you to make small features in silicon. For example, the extreme UV lithography. Then SADP means self-aligned double patterning. Then this is quadruple patterning. Okay, so all these things are being going on to actually push the Moore's law and is sticking to silicon. And if you say beyond silicon, what is the most promising? Obviously, the answer is not graphene. The answer is MOS2, because graphene doesn't have band gap, so it's not good for electrical devices. You cannot turn it off. Okay, so the best thing after silicon is MOS2 right now.
Okay, thank you very much. Actually, we are seeing that we are not going to finish, and we have many options also with silicon
Right.
and with silicon. So thank you very much. So I have another questions, but I am not asking now because we have many participants. So I am requesting you to, if you have any questions, so please ask.
Hello, can I talk?
Yes,
Yeah, yeah,
yes.
sure.
Thank you for your nice presentation. Okay, so I have two questions basically. One is if you see the performance, okay, so
Mhm.
for last 5 or 6 years, we are not seeing that much of change in our microprocessor performance. If you think
Mhm.
about the clock speed, okay,
Mhm.
so uh, why is that? Okay, so can you explain more? And another one is why basically the nanotubes they are failing. What is the big problem there?
Okay,
Thanks.
okay. So let me answer the first question. So, I mean, if we want to look at the performance benefits, right? Okay, actually, the focus has been now more towards portable devices. Okay, if you see the cell phones, okay, and your tablets, their performance have gone up over the years. In terms of the personal computing, like the ones we use in laptops or PCs, okay, that might have slowed down a little bit because the focus has shifted more towards making the portable devices faster, okay, and cheaper. So that could be one reason. And another reason is that uh, for the consumers, right, it's actually very hard to judge the performance based on only clock speed, because you should take other parameters into account, like the power dissipation, which is plays a big role that also should be kept in mind. So it's not just about clock speed, but if you look at maybe your devices in terms of energy efficiency, uh, you would see that they have become more energy efficient over the years, and thanks to the smart device architectures that is being played. And the second question that you asked is about why carbon nanotubes and all these are failing. So it's not just about failing. That's because when you want to make chips on a large scale, you need to have a process that is stable and that can be done on a large scale. Unfortunately, for carbon nanotubes or for 2D materials, this is not established yet. Normally, if you do it in a lab, you can do it very like nicely. One or two devices is fine. But if you make millions of chips, you need to make sure that all your chips perform consistently, and that is very difficult with the current process for carbon nanotubes, or in fact even MOS2. People use exfoliation mechanical technique which is not really good for large scale. So they're looking into CVD, but CVD technique still needs to be optimized for large scale production. Okay, so I hope that answers the question.
Thank you. Thank you for answering.
Okay, thank you very much. And so as we have the time limitation, so just we will take one more question. So if you have a question, please ask.
May I ask a question? My name is Dr. Sadid Munir. I'm from United International University.
Yeah, please.
First of all, nice talk, Dr. Mainul. Although I missed like most part of your talk, I just joined at the later part. So what is the current industry trend for these like non-silicon devices? Right? I mean, we have seen a tremendous amount of shrinking of these silicon devices, MOSFETs. But are the major player in the industry working on these 2D devices or carbon nanotube based devices?
At the moment, no. I mean, the answer is no. They're not looking into it. I mean, rather, they're looking into technologies where they can push the silicon even further. So one thing that the industry is heavily pursuing, and I mean, I was talking to some folks in Global Foundries and TSMC, and they're looking heavily on negative capacitance transistors right now. I mean, which is really, I mean, compatible with the current silicon process. And in parallel, if you say that some alternative options, then they're looking at 3-5 materials, but not I mean 2D materials at the moment. Okay. So 3-5 is an area that I know that Intel is looking into, and so does other semiconductor companies. So as a successor, as a possible successor of silicon, but not 2D.
Thank you.
Okay, thank you very much, Dr. Mainul Hossain and dear participants for your nice questions. So now we are at the end of the invited speech, and now I am requesting to our Qazi Ahmed Fuad sir for giving appreciation of the invited speaker.
Sir, Kabir sir, thank you so much. Sir, we want to share the appreciation at the end of the session as we have
Okay.
some limitation of time.
Okay. So now I am handling the floor to our session chair of Dr. Mainul Hossain and Assistant Professor, Department of Tripoli, University of Dhaka, to conduct the session. So Professor Mainul Hossain, the floor is yours. Thank you very much.
Okay, thank you, Dr. Kobi. So we have 6 papers in this session. The first one, the paper ID is 64, and the title of the paper is Effect of Underlap with Fixed Gate Length Gallium Nitride Based Double Gate MOSFETs. So I would kindly invite the speaker to present his talk. And if it's a recorded video, then maybe I'd request the organizers to play that, and then we can take the questions.
Islam from AIUB. Now I am going to present the effect of underlap with fixed gate length gallium nitride based double gate MOSFETs. Overview of presentation. Background: why gallium nitride based double gate MOSFET, device structure, simulation details, device parameters, result and discussion, and finally conclusion and future work. Background: impact of scaling of transistors and Moore's law, physical limits in scaling silicon MOSFET, new structure and materials for nanoscale MOSFETs, why double gate MOSFET. Impact of MOSFET scaling. According to the Moore's law, number of transistors on an integrated circuit just doubles every 1.5 years. So if you just observe the graph, it can easily visible what actually the Moore's law indicates. This is device millimeter versus the year. Future trend of semiconductor device. Moore's law in the past relied on shrinking in silicon MOSFETs. Moore's law in future demands more just shrinking the device structure. New materials and device structure integrated on silicon MOSFET. This graph just show the difference, show the characteristics between gate length versus year. Limitations. Due to poor electricity, opposite current increased. Due to poor channel transport, on-site current decreased. On-site current decreased due to SSD parasitic resistance. Gate leakage increased. Equivalent offset thickness increased due to gate depletion. Why double gate MOSFET? Higher current drive, that means better performance, professed to show higher tolerance to scaling, better integration feasibility, raised source drain structure, easy integration, larger number of parameters to tailor device performance. That's why we need double gate MOSFET. Why gallium nitride based double gate MOSFET? Because of this parameter, we need gallium nitride based double gate MOSFET, because gallium nitride based MOSFET actually indicates this parameter that is very useful. Electron mobility 2000, critical field 3, intrinsic carrier concentration 2 into the power 2, band gap 3.2, and saturated electron drift velocity 2 into the power 7. Therefore, gallium nitride is suitable for double gate MOSFET. This is the model analysis. The first one, A, is the proposed schematic without underlap length, and the second one, B, indicates with underlap length. This is the model analysis. Continue, and this is the proposed structure. Actually, this is the hafnium oxide as an oxide layer. Hafnium oxide is used, and this is gallium nitride. And again, hafnium oxide, since this is a double gate MOSFET, since there is two gate 1 and gate 2, and this one first one is without underlap, and the second one indicates without underlap, and the length for the gate is 8 nanometer. This is a table on simulation, device simulation scaling parameters. This is the units. LG gate length is value 8, the length of gate 8 nanometer. Then doping concentration in source to drain and or body is 1 into 10 to the power 15. Then effective mass is 0.18. Equivalent oxide thickness is 0.59. Supply voltage is 0.75. Then body thickness 3.1, and the length of underlap is 0 to 4 nanometer. Simulation details. Simulation has been performed using Silverberg Atlas device simulation package. Non-equilibrium gain functions is used as transport model NEGF. This is the simulated structure. This is the actually 2D structure that is found from Silverberg Atlas. This is the resultant discussion. This actually graph demonstrates the relationship between the drain current ID in milliampere range versus gate voltage. And this is due to the effect of underlap from 0 to 4 nanometer. This 4 color indicates from black color indicates 0. When 0 there is no the underlap is 0. Then this color, the second one is indicates this when the underlap is 1 nanometer. The third one, and the fourth one. Discussion and resultant discussion. The first one the first graph actually show the relationship between the on-state drain current ION in milliampere per micrometer versus underlap length, and the second one also discuss the off-state drain current I of milliampere per microampere divided versus underlap length. These two actually shows that in our proposed model the off-state current decreased when the underlap increased. Resultant discussion continue. This is the ratio on-state current versus off-state current and with underlap length. This figure actually, this curve actually indicates that an accordance with the increasing the underlap length, the on-state current versus off-state current ratio is increased. Resultant discussion continue. And now then conduction band. This is actually the conduction band. The first one, band energy versus the position along the channel X in nanometer range. And the first one is for the on-state current, and the second one is for off-state current. The conduction band energy actually represents here that there's 4 different color. This indicates they are different with different underlap length. Result and discussion continue. And this graph actually represents figure 7. It represents the drain induced barrier loading DIBL millivolt per volt versus underlap length. The variable of DIBL with the underlap length is observed. Result and discussion continue. This is the threshold slope SS millivolt per decade versus underlap length. This actually shows when we increase the underlap length, the SS, the subthreshold slope, also decreased. Result and discussion. And then the electrical field control plot for 8 nanometer gate length, this one for the on-state current and this is for the off-state current. These two actually represent the electric field that was found in Silverback Atlas. This is the methodology for the Silverback Atlas, the Go Atlas, then mesh, then region, electrode doping, then material. There are 4 contact interface models specific. This is the materials model specification. Then the NEGF transport model is used for calculation. The numerical method selection. This is the solution from log, solve, load, save, and then we can electronic plot and graph. Conclusion and future work. And performance investigation of gallium nitride based double gate MOSFETs. The evaluate on-state current DIBL, induced barrier lowering, subthreshold slope for a wide range of gate lengths. The SS performance is degraded because the bridge channel is away from the gate dielectric interface. The simulation of gallium nitride based double gate MOSFET for gate length 8 nanometer with symmetrical underlap was performed by using Silverback Atlas simulation software. The simulation results are precisely optimized in consideration of threshold voltage (VTH), threshold swing, SSI, on-state current, off-state current, on-state current, off-state current ratio, DIBL, induced barrier loading, and switching characteristics of simulated device. Impressive results was found comparing with previous research work also. This is the reference. Thank you, everyone.
Thank you for the nice talk. So I would like to invite questions from the audience.
Sir, there was no question from the audience.
Okay, is this speaker present? Anybody?
Yes, sir. The speakers are present.
Okay, so if there's no questions, I can probably ask one question. So, I mean, nice work. Very good that you investigated this underlap phenomenon. But did you try to calibrate your TCAD model against any experimental data? Is anybody here from the presentation?
Dear MD Rabiul Islam and dear
Yes,
Mainul Hossain.
my voice is clear, Polan sir.
Yes, we can hear you.
Yeah, we can hear.
Yes. So would you please repeat the question again?
So I was asking, like, did you calibrate your TCAD model against any experimental data? I mean, calibration means did you match your TCAD model with any known experimental data?
Yes, sir, we did before it.
Okay. So yeah, I mean, I didn't see it here. If you have done it, it's fine. Okay.
Yes, sir.
Okay, thank you. Thank you so much. Any more questions? Uh, if there are no questions, let's thank the speaker, and I think we can move on to the next one.
Okay, so thank you, paper ID 64. So now I would like to invite our next paper, the effects of substrate doping concentrations on 6H silicon carbide nanoscale GGN MOS ESD protection device.
Hello, I am Shiru Silicon Chowdhury. Today, I'll be presenting the effects of the substrate concentrations on 6-8 silicon carbide nanoscale GGMOS ESD protection device. The co-author of this paper is Mr. Farhadul Arifan. The outline of the presentation is as follows. ESD is the transfer of electrical charges between two bodies at different potentials, either through direct contact or through an induced electric field. So it's a charge-driven physical mechanism resulting from a charge imbalance. ESD events usually give a mild shock to human beings. However, if the same amount of ESD stress is injected into a microelectronic component, it could cause damage. Although ESD events are of very short duration, which is around 0.2 to 200 nanoseconds, the massive voltage pulse can give catastrophic damage to integrated circuits that cause the permanent failure of the device, as shown in figure 1. Besides these noticeable failures, minor levels of ESD shock can also generate latent problems within the devices, producing so-called walking wounded device. Walking wounded device reduces the lifespan and performance of the device drastically, as shown in figure 2. Based on the statistics of the ESD association in 2019, more than 25% of electronic devices are destroyed by ESD strikes worth around 5 billion USD a year. ESD protection circuits are significantly important to protect the internal circuitry of an IC against ESD strikes by providing a safe current path. They are placed on each I/O pin to shunt ESD current, as shown in figure 3. ESD protection devices with an IC must satisfy the requirements of an ESD design window, as shown in figure. The whole voltage should be greater than the normal operating voltage with some safety margin to avoid the latch-up problem. The trigger voltage should be less than the gate offset breakdown voltage to ensure the reliability of the device. Under the normal operating condition, the ESD protection device should be in the off state to ensure normal operation of the IC. The ESD protection device faces permanent damage when the ESD voltage and current reach to second breakdown, also known as thermal breakdown. Turn-on resistance is the change in drain voltage to the change in drain current when the ESD protection device is turned on during an ESD event. Literature review. Due to the continuous scaling of the devices with the development of state-of-the-art technological node, ESD is one of the major concerns in nanoscale integrated circuits. Many studies are being conducted all over the world on different protection schemes and materials to protect electronic devices against ESD strikes. Several configurations such as gate-coupled NMOS, grounded gate NMOS, silicon control rectifier commonly use ESD protection devices. The main limitation of FCR-based ESD protection devices is due to its relatively large trigger voltage and small holding voltage that cause latch-up issues. Furthermore, gate coupling NMOS forms a strong inversion channel in NMOS transistor due to coupled gate voltage. It makes the GC NMOS less effective to withstand ESD stresses. Another ESD protection circuit based on GG NMOS is widely used in the industries due to its compatibility with the CMOS technology, active discharge mechanism, low power dissipation, and simple construction. ESD protection devices are primarily based on silicon material. However, silicon-based devices inherently have some limitations. Silicon-based devices have a maximum operating temperature typically below 150 degrees Celsius. As silicon is a low bandgap material, the critical electric field needed to start impact ionization is lower than higher bandgap material, such as silicon carbide. Silicon carbide is a wide bandgap material that can function at extremely high temperatures up to 600 degrees Celsius. Being a wide bandgap material, silicon carbide has a low turnover resistance and pulse switching speed. As technology advances, new ESD protection devices are always necessary to restore the ESD levels to their previous performance level. Therefore, researches are being conducted on different qualities of silicon carbide to cope with the ever-shrinking technological nodes and ESD failures. Silicon carbide has multiple polytypes, out of which major polytypes are 3C, 4H, and 6H silicon carbide. These polytypes are widely used for commercial purposes. 6H silicon carbide polytype has the potential to be used as an ESD production device due to its high bandgap, high thermal conductivity, and high breakdown electric field. Objective. The main objective of our research is to mitigate the reliability problem and to increase the lifespan of the devices by protecting against ESD strikes. In this presentation, a gate grounded NMOS based on 6H silicon carbide having degenerated source and drain has been proposed. The effects of this substrate concentration on the snapback behavior have been analyzed. Design and methodology. The figure shows the proposed device structure. The gate length of the device is 28 nanometer. The material 6H silicon carbide is used as a substrate of the device. Multiple drain source and substrate contacts are used to reduce current density. At the edges of the device, shallow trench isolations are used to avoid leakage current among the adjacent devices. The figure shows the formation of lateral parasitic BJT in the GGMO structure. The structure of the device has finite effective resistance. During an ESD strike, the PN junction at the drain undergoes an avalanche breakdown. Holes flow from drain to the substrate, resulting in an increase in drain voltage, base voltage drop due to substrate resistance. Sufficient voltage drop between the base emitter junction of the parasitic BJT will turn it on. ESD current flows from the drain through source to ground. ESD stress at the drain of the NMOS transistor is released. To simulate the electrical characteristics of semiconductor devices, the Silverco Atlas device simulator is used. Denser meshes are used at the contact regions, the edges of the source, drain, substrate, and anterior regions of the device to improve the divergence problem of the simulation. To introduce easy stress on the design, usually using simulator properly, models related to carrier mobility characteristics, impact ionization, and recombination are used. Fermi model is used to estimate characteristics. Silverher model is used to include the impact ionization effect on the simulation. Simulation result and comparison. There are three different substrate doping concentrations are used. The source and drain doping concentration are chosen as 2E20 per cm cube. The figure shows that for higher substrate doping concentration, the trigger and hole voltage are higher. For the substrate doping concentration of 3E18 per cm cube, once the drain voltage is increased by around 7.75 voltage, the base emitter junction of the parasitic BJT becomes forward biased to turn it on, and consequently snapback occurs. The whole voltage for the substrate concentration 3E18 is 6.08 voltage. As the substrate doping concentration is increased, the trigger and hole voltage are found to be 9.52 voltage and 6.32 voltage respectively. When the substrate doping concentration is further increased, the trigger and hole voltage has increased to become 11.99 voltage and 6.89 voltage respectively. This figure also shows that the tunnel resistance for the substrate doping concentration of 5E18 per cm cube is the smallest among other results. Results in a better voltage climbing performance and improved current handling ability. From the band diagram, when there is no applied voltage, it can be seen that for high doping concentration, the potential barrier for electrons between source to drain is higher. Due to this higher potential barrier, electrons require additional energy to lower the potential barrier between source to drain terminal to start the drain current flow. Due to the abrupt rise in drain current, the drain voltage decreases, i.e. snapbacks. Therefore, for higher substrate doping concentration, the GGNMOS will trigger later compared to the lower doping concentration. After the snapback, the potential barrier between the source and drain terminal collapses, and electrons can easily flow from source to drain terminal. The table shows the summary of the results. For the doping concentration of 5E10 to the power 5E18 per cm cube, no thermal breakdown is found till 200 mA per micrometer. The table shows a comparative analysis between 28 nanometer GG-NMOS easy production device based on silicon at room temperature and the simulated data from our proposed 6H silicon carbide. Study shows that the minimum hole voltage of the GG-NMOS should be 1.25 times the normal operating voltage of the inch-on circuitry. Therefore, the normal operating voltage of the internal circuitry can be chosen around 5 voltage, as the whole voltage is 6.89 voltage for our proposed design. Conclusion. The effects of the substrate doping concentration of 6H silicon carbide based nanoscale GGNMOS have been investigated in this presentation. We can summarize our result finding as follows. It is found that an increased amount of p-type substrate concentration can lead to higher trigger and hold voltage of 6H silicon carbide devices. The Toronto resistance for the substrate doping concentration of 5E18 per cm cube is the smallest among other substrate doping concentrations, results in better voltage climbing performance and improved current handling ability. The thermal breakdown for the doping concentration of 318 per cm cube and 418 per cm cube are around 14 voltage and 100 milliampere per micrometer, whereas for the doping concentration of 5E18 per cm cube, the thermal breakdown voltage and current increases significantly. Therefore, the results show that the comparatively higher substrate doping concentration can be used to achieve higher trigger and hold voltage, which can be used for 5 voltage applications. These are the references we have used. Thank you. Any questions?
Okay, so thank you very much. So is there any author present in this?
Yes, I'm here.
Okay. So now I am inviting the questions from the participants. If you have any questions, please ask.
Sir, there is no question from the participants.
Okay. So just I want to know, do you have any plan to check your results with the other polytypes of silicon carbide, for example, 4Ace or the 3C silicon carbide?
Yes, I did it. I have actually written a journal where I have compared this with the 2,4H silicon carbide materials. That was for 70 voltage. To reduce the trigger voltage for my design, I have to use near punch through effect. Near punch through effect. Calibrated this result with silicon material published by Sealy. Which is also in 28 nanometer technology. That is what I use for calibration, and for silicon carbide 4H silicon carbide I compared, and that was published in ICREST transition.
Okay, oh, nice work. Okay, so thank you very much. So now I am inviting for next paper.
Okay, thank you. The next paper is paper ID 249, and the title is sub 20 nanometer gallium arsenide based cylindrical gate all around FETs for improved performance. I would request the author to present this work.
Hello everyone, this is Prince Joy Chakraborty. Today I will present my paper titled Sub 20 nanometer gallium arsenide based cylindrical gate-all-around FETs for improved performance. My co-authors are MD Mosabarul Islam, Raju Ahmed, and MD Iqbal Bahar Choudhury sir. At first, I will discuss about the table of contents. At first, I will discuss about why GS has been chosen for this research. Then our objective of this research, the Silvaco TCAD flow, information about our structure, then results obtained and discussion based on that, and then comparison with silicon based FET and comparison with ICREST data. As we can see from the first figure, the transistor count is increasing per year, so the technology node is also decreasing to fulfill the necessity of higher packing density, higher speed, higher performance. Now, to downscale the size, there are some challenges like short channel effects, AC dominates, threshold voltage decreases significantly, off current increases, subthreshold swing increases, on-off ratio decreases, both static and dynamic power increases. Now, how downscaling can be achieved without increasing power consumption? There are several ways. Using advanced structures like FinFET, double gate FET, TG-FET, lateral GA or vertical GA, or using high mobility channel materials, gallium arsenide, L-gas, etc., or using high K oxide materials. Now, why GAs is important material? FETs on 3V semiconductor would offer a number of advantages over silicon-based devices. Their higher carrier mobility leads high-speed logic operation. Their higher breakdown fields facilitates high power or temperature applications, and their ability of band structure engineering provides more design flexibility in integrated circuits. Of a number of 3V compound semiconductors, gallium arsenide becomes a choice of alternate channel material in place of silicon for decades because of their outstanding material properties and also the availability of semi-insulating gallium arsenide substrates. Moreover, the electron mobility in gallium arsenide is almost 5 times higher than that in silicon. Now I will discuss the objective of our thesis. To implement a gallium arsenide based GA FET to investigate its performance, compare the performance with conventional silicon based MOSFET and to what extent the device meet the ITRS requirement. Now I will discuss the basic SilvaCoTCAD flow. SilvaCoTCAD is a design automation software tools that models semiconductor fabrication and semiconductor device operation. If we write the command and give input in deck build, there will be an output structure file. Then Atlas will do the necessary simulation based on the structure file and plot using tectonic plot. We can also see from the block diagram here. It has built-in library for different semiconductor materials. We can characterize those materials in various analysis process. Also, it has different substrate materials and impurity materials. Here is our structural information and TCAD generated 2D slice of a GA FET. From table we can see that the source and drain material is gallium arsenide. Also channel material is gallium arsenide. For source and drain we used 5 nanometer of channel thickness, and for channel we analyzed 16, 14, 10 and 7 nanometer channel thickness. Our gate oxide was 0.6 nanometer and nanowire radius is 3 nanometer. Our doping information is also here. Now from figure 1, as both the transfer characteristics curves for HP bias and LP bias is almost parallel, so there is almost no DIBL effect in figure 1. For higher VGS, the HP curve deviates from the LP curves, mainly due to the higher electric field. From figure 2, the LP and HP curves of 16 nanometer and 14 nanometer is almost parallel, but when channel length is more shrinks, SC dominates slightly and thus curves deviates. We will see the effect of DIBL in DIBL analysis parts. Here we can see that in both energy band diagrams, as the channel length decreases, the drain depletion region extends more to the source depletion region and consequently tends to overlap this region. Extension or the overlap is more profound when the drain bias is higher. This overlapping reduces the barrier height when which is commonly known as drain-induced barrier lowering (DIBL). This can be happened either by the shrinkage of channel length or by the increase of drain bias or both. These bar graphs shows that when process length is 16 nanometer and 40 nanometer, the DIBL is almost negligible, and when it shrinks to 10 nanometer and 7 nanometer, the DIBL increases significantly. Here from figure A, the increase in the subthreshold showing as the channel length decreases as well as the bias increases. This increase is due to the increased flattening of the transfer characteristics curves as the channel length decreases and as the bias increases, which can be revealed from the transfer characteristics curves presented in previous slide. From figure A and B, as the channel length shrinks, the increase in the on current is less than that in the off current under HP bias, and the on current is almost insensitive to the channel length shrinkage under LP bias. This is due to the fact that the off current is governed by the DIBL, whereas the on current is limited by the transport mechanism, which depends on the carrier mobility as well as the carrier recombination in the gallium arsenide channel. So when channel length decreases, on-off ratio decreases. Here we can clearly see that the results of gallium arsenide dominates over silicon. We used a reference of recent works, and from the left side, if we can clearly see that the silicon results ion is less than gallium arsenide results, and I off is also tremendous in this work. On-off ratio is tremendously good, and SS is slightly low, whereas DIBL is almost 1/4. If we compare with International Technology Roadmap for Semiconductor (ITRS) data, except the threshold voltage and subthreshold swing for HP bias, we achieved all the parameters desired values required by the ITRS. Well, that is all I have for today. Let me now summarize what I talked about. GAF8 for sub 20 nanometer nodes has been implemented. Atlas based investigation has been carried out. Gallium arsenide is better than silicon and meets ITRS requirement. So thank you all.
Thank you. Very good presentation. Is the presenter here?
Yes, sir.
Okay, thank you. So I would like to invite questions from the audience. You can unmute your microphone and ask questions, or you can also type in the chat box. No questions?
No, sir.
Okay, so I have one question. So you considered sub 20 nanometer devices, right? So in your Silvaco Atlas modeling, did you consider any quantum effects?
Yes, sir.
Okay, so I mean, specifically, do you remember like what kind of model you used?
Sir, we used carrier zero model. As a method, we used carrier zero, and as a model, we used non-equilibrium Green's function and Schrodinger's equation and Poisson's equation to solve the current density of states, electric fields, number of electrons, and currents, etc.
And also, did you compare your results with the recent experiments, or how does it compare, you think?
Sir, we used a reference for a 10 nanometer device, and I think it's better than that paper.
Did you try also on FinFETs? Or just gate all around, right?
Yes, just get all around.
Okay, yeah, thank you.
Thank you, sir.
So if there are no more questions, then let's thank the speaker. And then we can move on to the next presentation.
Okay, thank you. Our next paper ID 309, finite element modeling of synaptic plasticity in mushroom type phase sense memory devices for application in neuromorphic systems. So I would like to invite the authors to present.
Sir, the next video presentation is quite long. Should we skip some of the part, theoretical part?
If the author
Hello, I'm here. You can skip the theoretical part if you want.
Thank you.
Thank you so
Thank
much.
you.
Hello and welcome everyone to our paper presentation, which is titled Finite Element Modeling of Synaptic Plasticity in Mushroom Type Devices based on the phase change materials for application in neuromorphic systems. I am Imtiaz Ahmed, student currently pursuing my MSc degree in Bangladesh University of Engineering and Technology, besides working as a lecturer in Brack University right now. And I worked with Nafiul Islam on this paper, who is not present here today, so I'm going to present this paper. I would like to take this opportunity to thank our supervisor, Dr. Mohammad Kausar Alam, Professor, Department of Tripoli Buet, who helped us a lot, who guided us to where we are right now and to publish this paper. He helped us a lot. We'd also like to thank all the organizers of this conference for accepting our paper and giving us an opportunity to present it before all of you. Big data applications, the amount of data involved is pretty high. These multiple to and fro, back and forth movement actually causes a large amount of energy consumption. But compared to the computers that we use, human brain actually shows a huge parallelism in terms of computation. And it's extremely fast in tasks like pattern recognition or speech recognitions. Say, for example, whenever you are seeing a picture of an apple, you can immediately recognize this as an apple. A computer needs to draw a lot of features out of it to eventually give you the result. The brain doesn't really work like that. Extremely low level of energy compared to the computers in these type of tests. Why is this happening? The fundamental reason is because brain is comprised of neurons and they act like the computation unit and the memory unit simultaneously. So basically, there is no need to transfer the data from the memory unit to a separate computation unit when your brain is working. Rather, in the neurons and in the synapses that connect multiple neurons are working as both the computation unit and the memory unit, and there is no to and fro movement, and that's why there is an extremely low power consumption. That's utilized to make it work like a biological synapse. In this work, we use a chalcozanide phase change material device, which is named GST. It's an alloy comprised of germanium, antimony, and tellurium. This material has showed reversible and rapid phase transition. For example, it has two different stable states. One is its crystalline state, another is its amorphous state. The crystalline state is well structured and it's low in resistance. On the other hand, the amorphous state has a very high resistance, and it all depends on the temperature it's operating at. Above 473 Kelvin, it works. It stays in the crystalline state, but above 873 Kelvin, it goes into the amorphous state. So there is a large difference in the resistance across those states. Also, there are a lot of intermediate resistance states across these two. So there is not only two resistance states, there are multiple. They can be used actually for in-memory computation applications. In this work, we actually try to alter their temperature by applying different pulse techniques, different voltage pulse that will create Joule heating, and this will eventually switch their temperature to achieve different resistance states. This is the device that we actually modeled in COMSOL multiphysics in the 2D axisymmetric structure, where the GST is actually surrounded by a top electrode and a bottom electrode of titanium nitride, and the whole device is surrounded by silicon dioxide. We've chosen to investigate two submodels for our simulation. One is programming and another one is read model. In the programming model, we will set the device by applying some pulse to a specific temperature, and by that we mean a specific resistance state, and this will be programming or reset operation. And the read model, we have to apply some voltages to actually read out the resistance state. It actually is in right now, so it is actually a set operation. So in the reset operation, we will have to increase the temperature so much that it actually crosses the melting temperature of GST, so it goes into the amorphous state, and the resistance is actually so high. And in this picture, we can see there is a wide, small line that's showing the temperature over the melting temperature, 873 Kelvin. This is the region actually going into the amorphous state, and above the other states are still in the crystalline stage. And on the right side, we can see the electric conductivity. The lower side of the GST region is actually showing a lower amount of electrical conductivity compared to the upper side. And for the set operation, we can see that applying a different pulse technique, we can actually achieve temperature lower than 873 degrees, so it still stays in the crystalline states. That means a higher electrical conductivity level. In this curve, we can see that applying different value of different amplitude of voltage with different pulse techniques, we can actually get a different amount of volumes that have a temperature over the melting temperature of GST. As the reset voltage value is increased from 2 volt to 4 volt, it requires less amount of pulses for the GST to be converted into the amorphous state. And in this case, we have actually used a staircase type of pulse that has its amplitude increased from 2 volt to 4 volt. And initially, when there is a 2 volt pulse going in, the volume of GST over the temperature, over the melting temperature, is too low. Whereas we move forward to 4 volts of voltage, the volume of GST over the melting temperature is actually dramatically increasing. Now, in the read model, we can see some really interesting findings. For example, in this case, we have applied a 0.8 volt pulse, but all with different pulse widths. We can see that even if we apply this set of voltages to the same initial resistance level, it will cause the GST to settle down to all different resistance levels. For example, the initial resistance level is 10 to the power 5 ohm over here. But as we apply those pulses, different pulse schemes actually causes the GST to settle down to different values of the resistance, and that's how we can achieve multiple stable resistance states by applying different pulse techniques. And in the second case, we can also see that we are applying a reset pulse. Okay, so the reset pulse, actually in our experiment, we kept the set pulse voltages value in the range of 0.5 to 0.9 volt. And for the reset operation, we have kept those values in the range of 2 volt to 3 volt. So whenever we are applying a 3 volt pulse, we are actually meeting the reset operation. So in this case, the 3 volt pulse is applied with different pulse widths, and the resistance is increasing as it should, because it's a reset voltage, and this high amplitude of voltage should increase the temperature so much that it will exceed the melting temperature and set the GST material to its amorphous state. So the resistance should increase, of course, but different pulse techniques or different pulse widths causes the GST to settle down to different level of resistance. And this is the same findings that we got using different types of pulsing schemes. For example, in the next slide, we can see that we have applied different reset voltages like 2 volt, 3 volt, or 4 volt with the same pulse widths. And we can see that with the variation of the pulse width or with the variation of the voltage value, amplitude, or with the variation of both, we can actually settle down to different resistance levels. And if we apply this same concept in the case of set operation, for example, if we apply a voltage value of 0.7 volt or 0.8 volt or 0.9 volt, as it's the set operation, the resistance should come down. It actually comes down, but depending on the voltage value or depending on the pulse width, it actually settles down to different resistance state. Initially, we implied this very thing, that phase change memory devices actually rely on this very property, that means the continuous transition between the multiple stable with the pulse width or the pulse voltage amplitude to get to the desired amount of resistance. After our simulations, we actually looked at the experiment done by Jaik Zoom and her team. They experimentally investigated the device behaviors with phase change memories, phase change materials, and they used a specific set of pulse to investigate their behavior. And we applied these similar network, the larger circuit, to make them work like the brains or the synaptic weight. For example, when we learn something, the synaptic weight is increasing, or when we forget something, the synaptic weight is decreasing. So for example, in the phase change memory devices, as the conductance or the resistance is going down or going high, they can actually be mapped to the synaptic weight update, or whether either potentiation or depression, and they can actually mimic the brain's function, the synapse function, to be used in further neuromorphic applications. So in this work, actually, we performed some comprehensive simulations on a mushroom cell PCM device in order to investigate its resistance behavior. And the resistance transition property, basically with different pulse techniques, actually show that they can mimic the way biological neurons or synapses work in terms of updating their weights as they learn things or forget things. This property can actually be utilized to design a broader crossbar type or some other type of neuromorphic network that can recognize patterns or recognize other things in terms of hardware. And that's how it can be extensively used in future energy efficient and faster computing. So that's all from our presentation. Thank you, everyone. If you have any questions, feel free to ask.
Okay, thank you very much for your wonderful presentation on phase sense memory and for neuromorphic applications. So now I am inviting the questions from the audiences.
Sir, there is no question from the audience in the chat box.
Okay, so I would like to ask, so what the material properties you have used? Is it constant or the temperature dependent properties?
Well, okay, first of all, let me take this opportunity to apologize for such a long video. So some of the parts might be misunderstood. Anyway, so we have used temperature dependent thermal conductivity as well as the electrical conductivity. They are both temperature dependent, and we take data from literature. Yes.
Okay. And how about the resistance contrast?
Sorry, I missed the question.
Yeah, how much resistance contrast you have? That means in the ratio of reset resistance and set resistance you have obtained.
Well, there has been an on-off ratio of about 10 to the power 4, in the range of 10 to the power 4 in our simulations. And it might be increased, but there is a problem when we try to increase the on-off ratio. There is a little bit of non-linearity that occurs in terms of, in case of phase change memory devices. So that's why there are alternatives, and we are trying to overcome those things in the work we are doing right now.
Okay. Okay, so thank you very much, and let's thanks to the presenter. So now I am moving to the next paper.
Yeah, thank you, Dr. Kubir. The next paper in this session is paper ID 378, and it's called the efficiency enhancement of PCDT-BT or PC7-1BM based organic solar cell through layer thickness optimization. So I would request the presenter to present this talk.
Really well in this pandemic. So today, hello and assalamu alaikum everyone. I hope you people are doing really well in this pandemic. So today I am going to present our presentation and on our research work. I'll try to give you some brief explanation of our work. Our topic is efficiency enhancement of a PCDT-BT PCBM based organic solar cell through layer thickness optimization. Welcome to my presentation. I am MD Mustaki Mia, a graduate student of the Department of Tripoli, UIU. I am presenting my presentation on behalf of my group. These are my teammates. They really gave their efforts on our very beautiful project, and our mentor was Dr. Iqbal Bahar Chaudhary, Associate Professor, Department of Tripoli, UIU. Main disadvantages is it takes a lot of place. For example, a simple rule of thumb is to take cells. So the advantages is high quality, low defect, and the efficiency is really high in terms of second and third generation solar cells. Challenges was to meet high consumption of active material, which is absorber. The second generation solar cell is thin film solar cell, which is CDT, cadmium telluride, copper indium gallium selenide, amorphous silicon. The advantages is high material utilization and the cost is so cheap. But the challenges was to meet scarcity or toxicity of some materials. Third generation, which is organic solar cell. So we worked on organic solar cell. The organic solar cell is dye-sensitized solar cells, polymer, small molecule solar cells. The advantages is non-toxic, abundant, low cost, short payback and transparent. So this is our proposed organic solar cell structure, and these are the thickness we consider for each layer in our work. So here is ITU. This is an anode. P dot PSS used as an HTL. PCDTBT PCBM. This is a bulk heterojunction material used as an absorber, and aluminium used as a cathode. So these are the thickness we considered throughout our entire project. Now moving to the results. technology computer aided design, it actually a computer simulation which develop and optimize semiconductor process technologies and devices. It works when structure file and command file are given to the Atlas simulator. It gives the log and solution file as outputs, and we can get the graph or curve using Tony plot. So this is our proposed organic solar cell which is implemented in TCAD. So here we use PCDTVT PCBM as an active layer, and the right one is the Venn diagram of our proposed OSI structure. Now moving to the results. We varied the important two layers, one is observer and the HTL layer. First, we tried to vary the thickness of observer, which is PCDTVT PCBM, to see the possible outcomes and the efficiency, but in that time we kept the HTL layer in a certain thickness at 30 nanometer, while varying the observer thickness from 40 to 500 nanometer. So we get those outputs. We can see when the thickness of the observer in between 40 nanometer to 150 nanometer, the open circuit voltage decreases, but when the observer thickness is greater than 150 nanometer, open circuit voltage increases. Then, when the thickness of the observer in between 40 nanometer to 150 nanometer, short circuit current density increases, but when the thickness of the observer is greater than 150 nanometer, short circuit current density becomes constant. For the fill factor and efficiency, while the observer is in between 40 nanometer to 220 nanometer, fill factor increases, but when the observer thickness is greater than 150 nanometer, fill factor decreases. Same thing happens with the conversion efficiency curve. Next, we kept observer thickness at 100 nanometer and varied the thickness of HTL from 0 to 40 nanometer. We get this result. We can see from the open circuit voltage curve while the thickness of HTL is increasing, open circuit voltage became constant. When for the short circuit current density curve, when the thickness of HTL are increasing, short circuit current density curve decreasing. For the fill factor and conversion efficiency, while the thickness of HTL increasing, fill factor becomes constant. The same thing happens with conversion efficiency, but it becomes slightly decreased and after then it becomes constant while the thickness of the HTL increases. Then we get the JV curve, optimized JV curve, where four different optimized curves are shown respectively without optimized, which is non-optimized. Here this is shown blue color is none, which is without optimized. Second one is HTL optimized, which is P.PSS. Third is observer optimized, which is PCDTVT PCBM. This is also known as active layer. And the fourth one is while the both HTL and absorber were optimized. So we saw the result of an optimized solar cell. We can clearly see the maximum efficiency are achieved when both are optimized. So here is the data are showing 4 different optimized results. Now moving to the concluding as our HTL layer, which can boost the efficiency over 8.8%. Our future work will be to boost the efficiency to our desired level. Now thank you and greetings to all of the respected people who worked very hard to successfully manage this wonderful conference. If you have any question or advice for our work, please inform us. Thank you. Thank you very much.
Thank you for the nice presentation. So I would like to invite questions from the audience, please. Is the presenter here?
Yes, I am here.
Okay. So any questions from the audience? No. Okay. So can you comment on the, so we know that organic solar cell is very promising, but there are also some concerns about the toxicity of organic materials, right? So can you comment on that, or for the materials that you have used, like are you aware of their toxicity?
No, I'm that not much aware of the toxicity of our used material, but we studied their band diagram and their some of the data which was needed for our project. So we collect those things and we got this results. So actually we worked on Dr. Shafiq's structure. So here he used P3HT PCBM as an active layer, which was a bulk heterojunction material. So we saw his efficiency was like 2.8%. So we actually changed the active layer and we move into PCDT PCBM as an active layer. So we actually got the efficiency is higher than Dr. Shafiq's efficiency. So we achieved like 8.8% after optimized. So we actually saw we used optimization because we actually got a certain nanometer. So where 220 when the when the layer thickness was 220 nanometer, we get the highest efficiency. So that is why we optimized. So as a certain layer thickness, we got the efficiency. So actually the absorber we used PCD to PCBM. That is why we used PCD to PCBM as an active layer.
Okay. Okay, thank you. If there are no more questions, then I think we can thank the speaker and move on to the next presentation.
Thank you so much.
Okay, thank you, Dr. Mainul sir. So now I am moving to the last presenter, paper ID 392, performance analysis of transition metal dichalcogenide based multi-channel cylindrical shape gate all around MOSFET. So I would like to request to present the paper.
Hello everyone, I am Mainul Hossain, author of this paper. Title: Performance Analysis of Transition Metal Dichalcogenate Based Multi-Channel Cylindrical Shape Gate All-Around MOSFET. Our paper ID is 392, and let's start. Here is the overview of we should maintain, or we used to maintain a variable definition, defining area and structure, adding oxide gate workflow. First, for initializing data, we use several steps: set of geometry, discretization scheme, mesh generation property, initial value boundary condition. After initializing data, we use the charge consumption, solve Poisson's equation, check for the convergence of Poisson equation, and to calculate the current, and collected our data for further analyzation. Now, here you can see. Now, here you can see oxide thickness variation with ion IO. The thinner gate oxide is necessary for the drain current. As a result, the oxide layer thickness needs to be small for a large amount of current. For a smaller value of oxide thickness, a large drain current will shift the value of the threshold voltage of the device to smaller values. Devices with a thick oxide layer have less control over the gate on the channel barrier height. Now, here you can see when oxide thickness decreases, ion IO increases. Here is the value for oxide thickness variation for subthreshold swing. We can see when oxide thickness increases, subthreshold swing increases. We used I forgot to say we used silicon, gallium nitride, and TMD as materials for channel material. Now, here is the channel length variation. In this figure, the ion-IF ratio is increasing from 7 nanometer to 23 nanometer of channel length, but when the channel length is further increased, ion-IF ratio is nearly unchanged. The reason is that when the channel length is smaller, the change in drain current is significant, but because of a small change in channel length results in a significant change in carrier density. But for greater channel length, the number of carriers does not increase proportionately. The number of carriers are structured for the current to flow. That is why the ion-IF ratio doesn't increase that much at higher channel length. Okay. Channel length variation with subthreshold swing. Shorter channel length channel draws higher leakage current, which increases subthreshold swing. Now, corona effect. First, we should know what's corona effect. The corona effect is known as a leakage current enhancement at the edges of the active areas in shallow, dense, isolated CMOS transistors. It usually deteriorates the transistor performance due to the symmetrical nature of our proposed device, the cylindrical shape of the gate and channel elements. The corona effect. The electric field, as shown in this figure, is uniformly spent in the circular rings within the channel. This provides better gate coupling, which improves the ion-IF ratio of our device. Now, here are the results for cylindrical shape all device electrical parameters for gate all around MOSFET, for molybdenum disulfide as TMD material, gallium nitride, and silicon. MOS2 multi-channel shaped gate-all-around MOSFET has better device electrical parameters than gallium and silicon as channel metal. We can see here it provides more ion-F ratio than gallium and silicon as channel material. When molybdenum disulfide used as channel material, it shows 52.65% and 56.19% decrease in subthreshold swing than gallium nitride and silicon respectively, as well as 26.47% and 37.5% decrease in threshold voltage. The percentage decrement of subthreshold swing and subthreshold voltage and higher ion-F ratio exhibits a MOS to multi-channel cylindrical shaped gate-all-around MOSFET as a promising candidate of MOSFET in sub 700 channel technology. Now, our optimized here is our optimized device structure and the values for silicon. You can see uh, it reduces a short channel effect, high ion of ratio. The value is for silicon. Less subthreshold swing, reduced corner effect, strong and symmetrical control over gate. Now you can see here. Now we saw MOS2 molybdenum disulfide of multi-channel cylindrical shape gate all-around MOSFET is show the best result from gallium nitride and silicon. And here is the advantage of using molybdenum disulfide: excellent electrical properties, high electrical conductivity, decent band gap, surface free dangling bond free from dangling bond, high effective mass of carrier, reduces the direct source to drain tunneling current, electron mobility nearly equals silicon here, and very thin structure. Here is the future plan for now. Validity of the device parameters should be checked by developing an analytical method. We are working on it. Monolayer TMC material can be used as channel material, and relative comparison on performance of such pH and biosensor can be investigated. The approach of simulator can also be applied for other types of device structure. Okay, that's all. Thank you everyone for being with me, and thanks. Yes.
Okay, so thank you very much, author, for your nice presentation. So, is there any author is present here?
Yeah, thank you so much.
Okay, so now I am inviting the questions from the audiences.
So I have one question. How did you simulate MOS2 in using Silvaco TCAD?
Thank you, sir. At first, I would like to add there is maybe there is a problem in my video because I had a slide with device parameters and details on device, but the slide was missing. But it's okay. So. What is the question, sir? Sorry,
Yeah, it's okay, Yeah, so I was just asking that how did you simulate MOS2 in Silvaco TCAD?
Yeah. Thank you, sir. Sir, didn't use Silvaco TCAD. We used console multiphysics, and we used a property from I wrote my literature. We you used uh, material property from different sources.
Okay, thank you.
Okay, so if there is no question, then we can finish the presentation part. And
Thank you, sir.
let's give a great thanks to the presenter and to the authors. So now I am requesting to Sujan Holadar sir for giving the appreciation for the inviting speaker and the session chair. So at first, I would like to give a great thanks and plaque of gratitude to Dr. Mainul Hossain, our invited speaker of ICREST 2021.
Thank you, Dr. Kabir, and thank you to the entire team at ICREST and AIUB for inviting me.
Actually, can I say something?
Yeah, sure.
Thank you, Sir Mainul, sir. I think I gain a lot from your presentation today. Can I contact you for furthermore for my project, actually my thesis, if you
Yeah, you
can?
can contact me. You can get my email address from the website and you can mail me. Yes.
Thank you, sir. Thank you.
Oh,
Okay, so now I am requesting to Sujan Holadar sir to give the plaque of gratitude for the session chair. Again, our Dr. Mainul Hossain for the session chair.
Sir, can you see the screen, sir?
yes.
But this is for invited speaker.
Okay, yes. Thank you so much, Dr. Mainul Hossain sir, for his time and for the for acting as an invited speaker and as also for the session chair. So we want to give you the appreciation, and here is the soft certificate for appreciation. You can see. So thank you again, Dr. Mainul Hossain sir.
Yeah, thank you. It's been a pleasure. Thank you.
Okay, so thank you very much. And now it's the
There is a photo session, sir.
photo
So
session.
I
Yes, please.
request everyone to turn on your web camera for the photo session. We have one photo session right now. So please everyone make sure your camera is turn off. Okay, please everyone turn on your camera. Okay, let me take the screenshot. Let me take the photo. One moment, please. I want to take another one. Thank you. Okay, thank you so much. Thank you so much for your time and for everything. Thank you.
Okay, so thank you very much, dear session chair and all the co-hosts and all the participants and paper authors and presenters. And just one announcement, after the session, please join in our inauguration ceremony in the ballroom, and already you have got the ID and the password. So I would like to request to join in the ballroom to the inauguration ceremony. And if the session chair, Dr. Mainul Hossain, give us the permission, then we can finish the today's meeting.
Yes, yes, I think we can conclude here. Thank you again, everybody.
Okay, thank you very much. Okay, goodbye, everyone.
Thank you, sir.